Hello and welcome to Tesla's Notebook, where we learn physics one step at a time. Today, let's study about derivatives and understand their geometric interpretation. So, let there be a function abbreviated by fn. Y is equal to f of x, which is defined over a certain interval. For example, the interval could be, let's say, x is greater than 0 and less than infinity, or x lies between negative infinity and positive infinity, etc., where x is called the argument and its values constitute the domain of the function fx. And the range of the function consists of the definite values of fx we get for each value of the argument x that we plug into the function fx, giving us definite values of y for every value of x in the interval or domain of the function fx. So now let's change x by an increment of delta x, which can be positive or negative. Then the value of y increases by delta y. Therefore, for x, the value of y is f of x, and for x plus delta x, the value of y will be f of x plus delta x. So therefore, to calculate delta y, we take the difference of y plus delta y and y, which is equal to f of x plus delta x minus f of x. Delta y here is the increment in the value of y corresponding to the increment by delta x in the value of x. Therefore, taking the ratio of delta y and delta x, we have, let's say, delta y upon delta x is equal to f of x plus delta x minus f of x divided by delta x. So the limit of this ratio when delta x tends to 0, if it exists, is called the derivative of the given function f of x. So this is the derivative, and it is denoted by f prime x or dy by dx. Therefore, f prime x is equal to dy by dx is equal to limit delta x tending to 0 f of x plus delta x minus f of x upon delta x. And this is our definition. If x takes some value, let's say for example a, then f dash x at a or f dash a or dy by dx at x is equal to a. Now this operation to find the derivative of a given function is called differentiation of the function. Next, let's try to understand derivatives geometrically. So let's see how to interpret them geometrically, geometric interpretation. Let's take a 2D coordinate system, the xy plane, x-axis and y-axis, and let's take a curve. And as we see, the secant is a line which intersects the curve at 2 points. When these points approach one another, the secant tends to behave like a tangent, touching the curve at a singular point. So as you can see, the secant, when moved, the points approached each other and they behaved like a tangent. Let's take a better look at this. Again, we have the xy plane and we have a curve with a secant between 2 points x, y, and x plus delta x, comma y plus delta y, whose coordinates we have indicated in the given graph, where delta x is the difference between both these x coordinates and delta y is the difference between both these y coordinates. And we see that the secant passing through the 2 points makes an angle with the x-axis, let's say phi, which is also the angle inside the triangle. Then delta y by delta x between the 2 points, let's call them m0 and m1, will be tan phi. Now suppose m1 approaches m0, then delta x will shrink and tend towards 0. It is denoted by dx called an infinitesimal. Similarly, as m1 approaches m0, delta y also approaches 0 and is denoted by dy, which is a minutely small quantity like dx. The secant then behaves as a tangent, and the triangle formed between the points m0 and m1 becomes very small, as can be seen. So let's draw it. And as you can see, the ratio dy by dx becomes equal to tan theta, where theta is the angle made by the tangent on the curve at m0 with x-axis denoted in blue. And tan theta is equal to dy by dx, which is f prime x. Therefore, tan theta is equal to limit delta x tending to 0, delta y by delta x is equal to f prime x is equal to dy by dx, which is the tan of angle, so tan theta, formed by the tangent line at point m0, x comma y, on the curve of the function y is equal to fx. So tan theta of angle theta formed by the tangent line at the point m0 of the curve y is equal to fx gives you the value of the derivative at the point m0 for the function y is equal to fx.